Hello, everyone. So today we're going to move into chapter 9, which deals with large sample test of hypothesis. So I think maybe a natural first question would be, okay, well, what exactly is a hypothesis test? Okay. So within statistics, what we found in chapter 8 was that we could estimate some sort of population parameter, let's call it mu. Okay. So we could estimate mu by creating confidence intervals. Okay. And we can do this with some amount of confidence, let's say 95% confident. And what we've learned was that this population parameter, although we didn't know the exact value, we knew that it would be between some sort of upper limit and then some sort of lower limit as well. Okay. Well, with hypothesis testing, what we could do is we can actually test claims. So let me write that down here real quick. So hypothesis testing. We test claims. So for example, let's say somebody claims that the price of their cars at a certain car dealership does not exceed $12,000. Okay, we could test that claim. We can determine whether or not somebody is, and I'm going to use these terms lightly, but we can determine if somebody's lying or telling the truth. Okay, now hypothesis testing is very similar to like what happens in a court trial. All right, so if you think about a court trial, all right, we assume. So when someone goes to trial, we assume that person is innocent. It is up to the prosecution to determine or to show or to demonstrate with some amount of confidence that the person is guilty. So we assume someone is innocent until proven guilty. Okay? Well, hypothesis testing kind of works the same way. Okay? The thing is, all we need is enough evidence to show that this person, and I don't want to use the word proven. I think that's bad. Until shown, I'm going to say this, not guilty. I think that's so much better. Because one thing we got to remember, and this is my fault, I should have used not guilty. Stats does not prove anything. It just gives you a snapshot of the data that you've collected at that moment in time. So when someone is on trial, we assume they're innocent until it's shown with some amount of evidence that they are not guilty or not innocent. All right? Now, in order for us to do this, and this is the beautiful part about hypothesis testing, it's very rigorous and there's a step-by-step process and it's repeatable. That is what science is all about. It's being able to do something over and over again and still getting the same exact results. So, a statistical test of hypothesis will consist of 5 parts. All right? The first part is what we call the null hypothesis. Now, this is denoted as H0, or some people say H0 or H0, okay? The second is the alternative hypothesis, and I'll explain what these are in detail down below. And this is denoted, and it all depends on the book or the professor that you have. It's going to be denoted HA or H1. The third thing you need is going to be a test statistic. And its p-value. Okay? The fourth is going to be significance level. and the rejection region. All right, and I'll show you what that looks like. And then finally, the fifth is going to be some sort of a conclusion. And I have a nice little flow chart that will help you to word your conclusion. So here are the 5 steps. This is what we do every single time that we do a particular test. Now, there are different types of hypothesis tests. There's a test for means. There's a test for deviations. There's ANOVA testing. There's linear regression testing. There's all these different types of tests that exist. All the tests, no matter which one your data dictates, will use these 5 steps. Okay? So here's our first definition. So I'm going to just pause the video, write it down, and then I'll explain it. All right, so here's our first definition. We have 2 competing hypotheses, the alternative, HA, and the alternative is generally the hypothesis that the researcher wants to support. Then you have the other hypothesis, which is called the null hypothesis, HO, and that's going to be a contradiction of HA. Now, we always assume that HA is true, okay? And if we do that, what we want to be able to do is show support for HA. In other words, we need to show that if HO is true and we want to support HA, which is our alternative, then we need to be able to show that the null hypothesis is false using some sort of sample data. And then we draw one of 2 conclusions. The first conclusion, reject the null. Or the second conclusion, we fail to reject the null. And that's basically what this is about. Now, I'm going to go back over this one more time, okay? If we assume the null is true, our null hypothesis, and whatever parameter we're looking at, will always equal some number. I don't know what that number is, okay? But the null hypothesis will always contain an equal sign. Always, always, always contain an equal sign. The alternative hypothesis, let me write it in a different color here. The alternative hypothesis will have the same exact parameter, except it's going to have some sort of different sign. So it may be less than, greater than, or a not equal to symbol with some value on the right-hand side. And it's going to be the same value as the null hypothesis. Okay? So the first thing that I want to do right now is I want us to get comfortable with labeling the null and the alternative hypothesis. Okay? So here's just a small example. And here's our first example. So you wish to show that the hourly wage of electricians in the state of California is different from $21, which is our national average. Okay? So if I wanted to go ahead and study this using a hypothesis test, I need to create 2 hypotheses. The null hypothesis, HO, and then the alternative hypothesis, HA. Okay, now remember, the null hypothesis always contains an equal sign. But the question becomes, what is the parameter? Well, since they're telling me $21 is the national average, I know average is a mean, and the population mean would be mu. So for both alternative and null, we're going to be using mu as our population parameter. Now, the null hypothesis always gets an equal sign. And then the alternative is either going to be less than, greater than, or not equal to. Well, there's one keyword in this entire statement, and it's different from. 2 keywords, I guess. Different. So if it's not equal to 21, then the alternative will be not equal to 21. Okay? And that is how we create our hypotheses. Now, if you read this one more time, you wish to show that the hourly wage of electricians in the state of California is different from $21, which is the national average. Here's what's happening in this problem. We are going to claim And I'll write it here. We're going to claim that the hourly wage is different. So what we need to do is collect data, and we need to be able to determine, will we reject the null or will we fail to reject? Now, to give you an idea of what's happening here, if our data supports whatever our claim, all right, if our conclusion is reject the null, then that means we can X this out, which means the data we've collected supports the claim, which, yes, the average hourly wage of electricians in the state of California is different, okay? However, if our sample data does not reject the null, in other words, if our conclusion is failed to reject, then our conclusion would be, you know what? The data we've collected shows that the hourly wage of electricians in California is not different than the national average. So that's what we're going to be looking at. We're going to be trying to do this type of hypothesis testing. Because if you think about it, people make claims all the time. But the big question becomes, well, how do you know they're telling the truth? How do you know what they're saying actually holds some weight? You do a hypothesis test. So the next thing I want to go over is, well, what do our tests look like? Well, since we're using large samples, recall from the central limit theorem that if you have large samples and you were to do a probability distribution, you would end up getting something that resembles a bell-shaped curve, okay? So within this bell-shaped curve, we know that right down the middle is going to be that population parameter. In hypothesis testing, all right, we can have 3 types of tests. The first test is going to be what we call a two-tailed test. So what I like to do is just highlight my regions. Now, those regions that I highlighted are called the rejection regions. The middle, since it's not shaded, would be fail to reject region, okay? Now, how do I know that's the type of test I have? The alternative hypothesis will always determine your test. So, in this situation, our alternative hypothesis, boy, that's a tongue twister. You know what? I'm going to use the number above. So if your alternative hypothesis is not equal to, you will have a two-tailed test. Okay? Now, for the other two, if your alternative hypothesis is less than some number, then you will have a left tail test. All right, and remember, the shaded region is always your reject region. The unshaded is fail to reject the null. So that's a left tail test. And if you think about it, look at the inequality symbol. It's pointing to the left. The final one is if your alternative hypothesis is greater than some number, then you will have what we call a right tail test. So you still have your rejection region. You still have your fail to reject region. And this is called a right tail test. And now just like in confidence intervals, okay, wherever you have that line that separates the fail to reject from the rejection region, that is called a critical value. So I'll just abbreviate it with a CV. And then on this very last one here, I'll write the critical value. Okay? So that critical value separates the regions from reject and fail to reject. Okay? Now, in order to determine a conclusion for the test, there are two ways to do this. So let me just write a statement here. So to decide whether we reject or fail to reject the null, there are two ways, and I'll show you both. In fact, I do them in every single problem. Okay, the first way is by using a test statistic. And then the second way is what we call the p-value method. Both are decent methods. The p-value method is really good if you're using technology, okay? Either way, you're going to get the same exact result, okay? Now, excuse me, for this chapter, okay, we're going to be testing population means. That's what we're going to focus on. Once we understand how the test works, remember, this will apply for any type of parameter you're looking at. So the easiest one that we want to focus on is just testing population means. Now, our test statistic for mu is going to be the following, okay? So Z is going to equal x bar minus mu all divided by sigma over the square root of n. And remember, if n is greater than or equal to 30, then we can use the standard deviation as well. So these are the two formulas that we're going to use. Notice they are the same exact thing. The only thing is different is that if we do not know the population deviation, as long as we have a large sample, we can substitute S for that and call it a day. Okay? Now, the last thing I want to go over is going to be how do we find these critical values? Okay, because remember, we have, for example, we have this bell-shaped curve. And if it's a left-tail test, I told you this number, whatever this happens to be, is a critical value. Okay? So critical values are dependent on a level of significance, which we've already talked about that in when we talked about confidence intervals. So alpha is going to be equal to, and these are the most common, okay? Alpha will equal 0.01, 0.05, or 0.10, okay? And if you think about this, when we were talking about our confidence levels, when we were doing our confidence intervals, that would correspond to a 99% confidence level, a 95% confidence level, or a 90% confidence level, okay? But the thing you got to be concerned with here and what you got to be careful about is that with confidence levels, you always had two tails. However, with hypothesis testing, the alternative hypothesis will dictate what type of test you're doing, whether it's left tail, right tail, or two tail. So you got to be careful. Now, let's talk about what alpha represents. Okay? So alpha represents our significance level, but more importantly, this represents the risk that you are willing to take of making an incorrect decision. If you reject the null, okay? So alpha represents the risk you are willing to take of making an incorrect decision if you reject the null. In other words, the way that you can think about alpha is, okay, this is the amount that I'm willing to risk by sending an innocent person to jail. Okay? So if you think about somebody that's on trial, you are willing to be incorrect this much even if they go to jail. Okay? So that's why this significance level is very, very, very important. Okay? Mathematically, alpha equals the probability of falsely rejecting HO, which is the same exact thing as saying the probability of rejecting HO when it is true. In other words, you are sending an innocent person to jail, okay? It's the maximum tolerable risk, all right? Because remember, nothing is perfect, and stats doesn't prove anything. The only thing stats will do for you is it provides you a snapshot of what is happening with your data at some moment in time. So that's going to be it for this lecture. In the next section, I'm going to go over a very systematic process on how we actually conduct a hypothesis test. And I'm going to do a bunch of examples so you can see how it works. Okay? See you in the next video.